Major funding for Earth Revealed was provided by the Annenberg CPB project.
The rich diversity of landforms and geologic activity on Earth make it unique in our solar system. 3 decades of space exploration have taught us that most of our neighboring planets are geologically stagnant when compared with the dynamic Earth. Until very recently, geologic phenomena such as earthquakes and oceans, volcanoes and glaciation were thought to be unrelated aspects of nature. But in the 1960s, Earth scientists had a bold and revolutionary realization that completely changed our concept of the Earth. They surmised that these diverse geologic phenomena could be explained by a single unifying concept, a blueprint of global geologic activity called the theory of plate tectonics. Plate tectonics is built on the premise that the outer skin of the Earth is composed of individual slabs, or plates. These rigid plates, which can be continental in size and in some places hundreds of kilometers thick, slide around on a partially molten mantle layer below. Where the plates collide or move apart or slide past one another, a great variety of geologic activity results. Ocean basins open and close, mountain belts emerge, and volcanoes erupt, all accompanied by countless earthquakes and the formation of new rocks and landforms. Although we still have a great deal to learn about the mechanisms in the Earth's interior which cause the plates to move, most scientists agree that the concept of plate tectonics is valid.
Today, the theory of plate tectonics is widely embraced, but the road to its acceptance was long and at times fraught with controversy. During the 15th century, Europe began its great age of exploration. As navigators charted coastlines the world over, scholars became intrigued by the similarity between the Atlantic coasts of Africa and South America. In 1912, scientist Alfred Wegener introduced his theory of continental drift, which sought to explain this similarity.
Alfred Wegener is one of the individuals who in the 20th century has had a major influence on geological thought. He observed, like several before him, the geographic relationships along the Atlantic Ocean, and that the obvious match between particularly the African and South American continent. This led him to conclude that the surface of the Earth, that the continents were not stable but in fact mobile, and led to his idea of drifting continents. At the time it was not accepted. It was not well accepted in either geological or other scientific thought, but ultimately became the foundation for what was a real revolution in geology.
Wegener pored over geological maps that showed identical rock types, fossils, and mineral deposits in many different lands. He was intrigued by what he discovered.
He began to see that certain patterns matched up if you carried them across major ocean basins, particularly in the southern hemisphere continents, or what we now call Gondwana, which is split apart into Antarctica, Australia, South America, and Africa. What he found is that certain plant fossils matched up very nicely on these different continents. He found certain climatic zones, glaciation zones or coal bed zones, matched up on these various continents, and they didn't make sense with where the continents are today in terms of the current climatic zones.
When he fit Africa against South America, Wegener discovered that the rocks of a South African mineral belt coincided with similar formations in Brazil. A South African mountain range, ending at the coast, lined up nicely with a similar range in Argentina. Furthermore, the areas of ancient rock in Africa formed a continuous belt with those in South America. Wegener wrote, "It is just as if we were to refit the torn pieces of a newspaper by matching their edges, and then check whether the lines of print run smoothly across. If they do, there is nothing left but to conclude that the pieces were in fact joined in this way."
So Wegener really put together the story for all the continents and wrote it down and collected all the evidence that he could about it. And so that's partly why we hear so much about Wegener, because he brought it all together.
Wegener's suggestion that the continents had once been joined and drifted apart to their present positions ignited a major controversy in the scientific community. Acceptance of Wegener's continental drift theory seemed to be divided roughly along hemispheric lines.
I think the geologists who were working in the southern continents never had any doubt, because the evolution of species is so clearly parallel on them, and they have so many other geological events that are in common between the South Africans and South America and India and Antarctica once we began to explore it, that there was just no doubt that they were all parts of one piece. But most geologists weren't working in the southern continents. They were working in Europe and North America, and they just didn't catch on.
Many scientists were especially disturbed by Wegener's explanation for how the continents moved apart.
Wegener explained his theory of continental drift based on the fact that the continents were moving through the ocean basins, and the continental crust was basically plowing through this oceanic crust. Geologists at the time could not understand how the rigid, tough continental assemblies could plow through the weak oceanic basins, and still it was the continents that were deformed to make mountain ranges. That seemed rather peculiar.
According to Wegener, the mechanism behind continental drift was the centrifugal force of Earth's rotation and the tidal drag of the moon and sun. Geophysicists quickly and correctly exposed the flaws in this reasoning.
In fact, the most difficult aspect of his theory was that he alluded to a centrifugal force as explaining why, in fact, the continents drifted. It was shown quite conclusively that the forces were too small, the rocks were far too strong for this to have been the case. So people were able to reject his hypothesis completely at the time, based on a mechanism which, in fact, was shown to be incorrect.
Because Wegener's explanation for why continents drift did not hold up, he couldn't convince most other scientists that the continents had, in fact, ever drifted at all.
Some people like to say that scientists are so fuddy-duddy they refuse to let any new idea come in. And I think that's a bad way to think about this. We really are careful, and we don't want to leap on some glamorous new idea unless our data really does support it, and our understanding of how the world works really can incorporate that. So I think we really did not have any data that was so cutting and so clear that we had to accept this theory. And so I think they were actually being responsible, they were being conservative, but they were also being responsible scientists.
In 1930, Alfred Wegener died of a heart attack while attempting to cross the Greenland ice cap. By the 1940s, with a lack of any conclusive evidence, the heated arguments about continental drift cooled off. Wegener's theory, however, would soon once again be propelled to the forefront of scientific debate, but in a most unexpected way.
In order to understand continental drift, we really needed to know how the oceans are made and destroyed. And we had very little understanding at all, even the shape of the seafloor. And so we really needed some new technology. Oceanographic ventures are very driven by technology. And it turns out, I hate to admit anything was good about World War II, but it was very good for developing new technologies.
This new technology developed for World War II included the fathometer, an echo-sounding device that instantly measured depths to the sea floor, enabling troop ships to move into shallow water. One transport commander, Harry Hess, made a habit of running his ship's fathometer continually. A geologist and Princeton professor in civilian life, Hess wanted to learn more about the topography of the sea floor. He soon discovered that the ocean floor was not level as expected, but was instead dotted with flat-topped mountains, which he named geos. Hess was perplexed by how these mountains formed. Their flat summits could seemingly be explained by wave erosion, but why then did the geos lie so deep underwater? Hess thought he saw a clue to this mystery when he observed that the deepest geos lay farthest from the mid-ocean ridge system. Hess and a colleague, Robert Dietz, suggested that geos are in fact wave-eroded islands which submerge as the crust beneath them subsides. To account for this subsidence, they proposed a radical new theory which they called seafloor spreading.
Harry Hess had a bold, imaginative concept which he enunciated in 1962. It stated that the newly found Mid-Atlantic Ridge was actually the site of upwelling mantle beneath the ridge, and that it solidified, the melts derived from it solidified at the ridge. They were carried laterally, piggyback away from the ridge, much as the froth in a pot of convecting stew would be carried away from the central upwelling current. What Wegener had evoked was continents floating on and plowing or drifting through ocean basins. What Hess and others showed was that the ocean basins themselves were growing from the mid-oceanic ridges, and that over the course of time they enlarged from the ridge and spread laterally. These would then be capable of carrying the continents initially much closer together and actually joined at the onset at the ridge, away from one another, directly away from one another by the spreading process. The combination of continental drift and seafloor spreading then gave them both the mechanism and the manner and timing in which the continents had drifted apart from one another.
If mid-ocean ridges were continuously creating new sea floor, it would seem that the Earth must be growing, swelling along the ocean ridges like a ball slowly being inflated. But scientists saw no convincing evidence for an expanding Earth. How then could the excess oceanic crust be explained? Hess suggested that the ocean floor simply sinks back into the planet at deep marine trenches. He claimed that this process, now called subduction, destroys the surface formed by seafloor spreading. Just as Wegener's hypothesis was weakened by lack of data, so too was the model of seafloor spreading. Hess cautiously referred to his own theory as geopoetry, but supporting evidence would come from the emerging field of paleomagnetism.
Well, the term paleomagnetism refers to ancient magnetic fields of the Earth. We can say something about ancient magnetic fields of the Earth because of the record they leave in rocks. Many rocks become magnetized when they are formed, or sometime after they are formed. When they become magnetized parallel to the Earth's magnetic field at that time. So if you can collect a rock sample, measure which way it's magnetized, and determine when it was magnetized, then you can learn about the orientation of the magnetic field at that time in the past.
By the early 1960s, Geologists were mapping the magnetization of rocks worldwide. One startling discovery came from the ocean bottom, where oceanographers discovered an unusual pattern of strong and weak magnetic stripes in seafloor lava. Cambridge University student Frederick Vine and his advisor, Drummond Matthews, were especially intrigued. Two questions fascinated them. What causes the strong and weak parts of the magnetic patterns? And why is the pattern striped? They soon realized that the changing intensity of the pattern was caused by the reversal of Earth's magnetic field.
The evidence we have that the Earth's magnetic field has been reversed in the past is simply that we find rocks, old rocks, that are reversely magnetized. That is to say, they are magnetized pointing south rather than pointing north. There was much scientific debate at first, because it's known that some rocks can be placed in a magnetic field pointing one way and become magnetized exactly opposite to that direction. And the fact that such rocks existed meant that it was possible that reversely magnetized rocks were simply recording normal magnetic field. The clinching evidence came when scientists from the U.S. Geological Survey and from other places went on expeditions around the world, collected rocks of different ages, and were able to show that rocks collected from around the world of the same age always had the same polarity. Rocks that were younger than 700,000 years old were normally magnetized. Rocks older than 700,000 years were reversely magnetized. This global pattern of magnetic polarity recorded in the rocks is what convinced people that it was the magnetic field itself changing polarity.
Vine and Matthews noted that the striped reversal pattern is parallel to mid-ocean ridges. By 1965, they concluded the best way to explain this relationship is by seafloor spreading. To check their conclusion, Vine studied the magnetic stripe pattern across several mid-ocean ridges. He predicted if seafloor spreading did occur, the magnetic pattern on one side of a ridge should be the mirror image of the pattern seen on the other. With startling precision, Vine's prediction proved correct.
Vine and Matthews figured out this idea and published it in a kind of an obscure paper to start with. But then when Fred Vine collected enough profiles across different mid-ocean ridges and saw that it really was true, he went on the road and he was talking about it to anyone who would listen. And in December of '66, he gave a lecture at Scripps Oceanographic Institution that just changed the whole direction of the institution. I arrived there as a graduate student in January of 1967. I thought I was coming to this venerable old oceanographic institute that everybody would be a little bit bored, and they were just crazy. There were records strewn out on the floor all over the halls. Everybody was just all in a chaos over this new idea. It meant a total different way to explain almost everything on the seafloor.
A further test of the seafloor spreading hypothesis was carried out by geophysicists J. Tuzo Wilson and Lynn Sykes. They were interested in the faulting which offsets mid-ocean ridges. If a feature such as a road or fence is split and moved by an earthquake, one can deduce how the crust shifted along the fault by measuring the direction of movement and the amount of offset. Many scientists expected the same to hold true at faults cutting across the mid-ocean ridges. But Wilson and Sykes pointed out that if new crust is forming at ridges, then growing seafloor should shift along the faults in the opposite direction. Based on his study of seismic records from the mid-Atlantic ridge, Sykes concluded that this, in fact, was taking place. Wilson and Sykes named the new class of geologic structure transform faults, which served as further proof of seafloor spreading. As transform faults were being discovered, oceanographers prepared for the most intensive sampling of the sea floor ever undertaken, using the research vessel Glomar Challenger. In 1968, drill cores showed that the sea floor grows older with distance from the mid-ocean ridges. Together with the magnetic data and transform faults, the cores indicated sea floor spreading must take place. Suddenly, scientists could easily explain many aspects of Earth's geology and history which had long been unclear. Not only could the distribution of fossils and paleoclimates be explained, but the origins of mountain ranges, mineral resources, large faults, and magnetic field patterns also made sense. Geologists realized that Earth's surface is divided by the system of mid-ocean ridges, subduction zones, and faults into giant plates which slowly separate, converge, or slide by one another. In 1967, Donald Mackenzie and Robert Palmer introduced the term plate tectonics to describe this revolutionary view of our world.
I guess you could say that the emergence of the concept of plate tectonics is an example of the scientific method in action. We use a great number of kinds of observations, all different, all seemingly unrelated, and bring it together in a model that explains everything. Prior to the advent of plate tectonics, we knew that we had mountain ranges, but we didn't know why we had mountain ranges. We didn't know why there was this incredible shortening. We knew that we had volcanism near the margin of the continents. We didn't know why. These things are explicable based on plate tectonics. And it is the fact that this new model, this new paradigm, resolved so many divergent, seemingly unrelated geologic facts, observations that we already knew, that allow us to move forward to a new level of understanding.
Plate tectonics has become one of the major unifying theories of earth sciences. In many ways, it's comparable to the theory of evolution in life sciences. It provides that unifying theme upon which we can understand, and by which we can understand very wide array of processes which are taking place in the Earth's crust. And so I think it's quite clear that it is probably the most important contribution which has been made to geological thought in much of its development.
Plate tectonics theory fundamentally changed the way Earth scientists view our world. Acceptance of the theory has taken hold worldwide, although a few skeptics remain.
There are skeptics to every theory, and I guess you would have to say whether we're talking about evolution or a spherical Earth. You'd have to say there are skeptics. There are people, I'm told, who don't believe that the Apollo mission actually went to the moon. My belief is that it is a very healthy thing that there are such skeptics, because they test our honesty, basically. It's the emperor has no clothes sort of phenomenon. We all believe in a new hypothesis and accept it so completely that perhaps we don't test where we should. And it is very important that these skeptics exist.
Although plate tectonics explains many geological phenomena, certain questions about how it actually operates remain. Earth scientists are still trying to understand the mechanics of tectonic activity.
In terms of the next challenge of plate tectonics, it really goes back to the initial debates back to Wegener's time, which centered on the actual driving mechanism. We know that the Earth is convecting and that the movement of the plates is related to this convection. We don't really understand the dynamics of the convection very well, whether or not the updrafts are actually driving the plates apart, or whether the colder parts of the plates that are being driven back into the mantle are actually pulling the plates apart, or whether it's some combination of the two. So it's this question that a lot of debate is focused on right now. In terms of the more surface level processes, I think the major advances or frontiers really deal with rates of processes. How fast do certain plates move past one another, and how rapidly does that cause mountains to form, basins to drop down, basins to turn back into mountains.
The plate tectonics revolution has had a profound impact on our view of planet Earth, even extending beyond the field of geology.
The theory of plate tectonics has been, if not instrumental, certainly one of the major contributors to us increasingly looking at the Earth as a single system and all the components of it as being an interrelated part of that system. And our increasing understanding of environmental systems is essentially a follow-through of that basic theme, and something that's been very, very necessary.
By the late 1960s, seafloor spreading and the concept of continental drift had gained wide acceptance. Eventually, they were combined into a global model of crustal dynamics that revolutionized geology. The theory of plate tectonics has had a pervasive impact on the Earth's sciences. It's demonstrated that earthquakes and volcanism, mountain ranges and ocean basins are all interrelated, that they are the consequences of tectonic activity at plate boundaries. It's provided new perspectives and imposed new constraints on all geologic interpretations. And the theory of plate tectonics has shown the geologic diversity and activity of Earth to be the consequence of dynamic tectonism that's been functioning for billions of years. Most current research in plate tectonics focuses on documenting the movements of plates in the earliest periods of Earth history and on understanding the mechanisms of plate formation and movement. These mechanisms operate in a most inaccessible place, deep within the Earth's mantle. Unraveling the dynamics of the mantle and its link with the plates is one of the most formidable and exciting challenges facing geologists in the future.
Major funding for Earth Revealed was provided by the Annenberg CPB project.